Sorry about that. I got cut off. So I was in the middle of trying to prove to you that these two blue angles are the same. Okay, ask me about it if you're not sure about why they should be the same, but hopefully you can prove it to yourself pretty easily using geometry. Okay. The next thing I wanted to show you was how to set up a force body diagram for this situation. So remember that AC and actually the middle of the curve is to the left in this picture. Okay, and I'm going to outline our hill in orange just so you have a sense of like, this is our hill. The car is sitting on this hill. It's going around a circle, so it would be like heading into the page and making a turn and coming back out and heading back into the page. Okay, so we need to set up a force body diagram, or sorry, Newton's second laws for this situation. And the question we're really getting at is how fast could someone be moving? And yeah, this is all in variables, but we can still solve for it in terms of algebra. And I want you to be really comfortable solving for things in terms of algebra. Okay, so in this situation, we only have one force acting in the x direction, and that is Fnx. Okay, so Fnx is pointing in the same direction as AC. Okay, and in this picture, it's to the left, so it's negative. We have minus Fnx is equal to Ax. Okay, we know the size of Ax is going to be Vt squared over r, because Ax is AC, but it's pointing to the left, so we have a negative sign. Okay, with that though, our two negative signs we can cancel out when multiplying by -1 on both sides. And so we have Fnx equals mVt squared divided by r. Now, because Fnx is directly across from this angle, we can write Fnx is Fn times sine theta. Okay, so Fn sine theta is equal to mVt squared divided by r. Okay, we can't really do that much more because we don't know what Fn is. And for that, we're going to look to the y information. Okay, so in the y direction, we have Fny, which I just drew in, and Fny is directly next to our angle, so it will be Fn cosine theta. But I'll just write it out as Fny, which is the second red arrow I drew, minus Fg equals May. And as long as the car is not slipping, it is not moving up and down at all, Ay has to be equal to 0. So I have Fn sine theta, or sorry, cosine theta, minus Fg, which is mg, is equal to 0. And I can solve for Fn. All I'm going to do is I'm going to bring mg to the other side. I'm going to divide both sides by cosine theta, and I find that Fn is equal to mg divided by cosine theta. Okay. Now I can take this and I can put it in for my Fn up here. Okay. So I'm going to go to the next page, but I'm going to bring these two equations with me. Alright, so these are the two equations I brought with me, and remember, at the end of the day, we want to find Vt. Okay, so I'm going to name these. I'm going to name these equation 1 and equation 2. So I'm going to plug 2 into 1 because I've solved for Fn, and I can write mg cosine theta, or sorry, mg divided by cosine theta times sine theta equals mvt squared divided by r. Okay, I'm going to divide both sides by m, so I'm going to divide by m, and you can just put something in the denominator. That's the same thing as dividing. So I'm canceling out my m's. And then the last thing I need to do is get rid of this r, so I multiply both sides by r. Okay, and I'm going to rewrite this as gr and then times sine theta divided by cosine theta. And you should be saying, aha, sine theta divided by cosine theta is really tan theta. So I have gr tan theta is equal to, and all I have left is vt squared, so the r is canceled out, so this is equal to vt squared. My very, very last step is to take the square root, which will cancel out the squared, and I have vt is equal to the square root of gr tan theta. Okay, and this should look kind of familiar. This is a lot like what you got in the CalLab. Okay, but remember, this was a situation without friction. So the next thing I'm going to show you is how to deal with a situation when you do have friction. Okay, so the next thing we're going to do is we're going to deal with a situation where we have friction, but before I outline the process for you, I want to ask you a question. Should FF point up or down the hill? Okay, I want you to take a minute and try to answer that and try to justify why you think it should point up the hill or why you think it should point down the hill. Alright, so now that you've taken a minute to think about this, I want you to think about being in a car on a highway. Okay? If you are rounding a curve, and remember, in this picture, this is a side view. The center of the curve is this way. Are you more likely to slide out or in? You're more likely to slide outwards. And if the road is more slippery, the more likely you are to slide outwards. What that tells you is that friction actually points down the hill. Okay, so FF helps you. To not fly away. Okay, so the next thing I want to do is I want you to, using this force body diagram, I want you to try to find what is the maximum Vt if you have friction. And let's say if we have a coefficient of static friction mu, and you still are going around a banked curve. So kind of like I just did, I want you to use this force body diagram, okay, use Newton's second laws, and try to figure out what is my maximum Vt. Alright, so go ahead and try to do this. Try to at least write out Newton's second law, and then come back to this video. So now that you've done that, we have sigma fx equals max. Okay, again, we're using this as our x direction and up and down as our y direction, not the weird heel x and y. And the reason we're doing that is that AC is straight in the x direction. So in the x direction, we have two things. We have fx, and we have fnx. So ffx and that's to the left, minus Fn x is equal to max. Remember, ax is ac, so that's equal to m vt squared divided by r. Now, we know that ff is equal to Fn times mu, and that the x component, if you look at it right here, I'm going to draw it in red, is next to the angle, so that will be times cosine theta. Remember from our last force body diagram that Fnx is opposite, so that will be times sine theta. Okay. Again, we can't do anything yet because we don't know a number for Fn, but I'm actually going to factor Fn out, so I have minus Fn, and I factored the minus sign out, equals cosine theta times mu plus sine theta. Okay, and that's all equal to m vt squared over r. Now in the y direction, we have three forces. We have Fny minus Ffy minus mg equals 0. Okay, so we have Fn cosine theta. Okay, I'm going to draw this. So the yFn is cosine theta because it's right next to the angle, minus mu times Fn, and that's going to be sine theta minus mg equals 0. Okay, and I'm actually going to go ahead and just bring mg to the other side. So I added mg on both sides, and this is all equal to mg. And again, I'm going to factor out an Fn, and I get cosine theta minus mu sine theta equals mg. Okay, my last step is kind of a brutal step. I'm going to divide both sides by cosine theta minus mu sine theta because I want to get Fn by itself. So divided by cosine theta minus mu sine theta. Okay, and what I find is that Fn equals mg divided by cos theta minus mu sine theta. Okay, now what I can do, and I'm going to bring this to the next page, is I'm going to use these two equations, and I'm going to use them to solve for Vt, just like I did before. Alright, so I have these two equations. I'm going to take this and put it in for Fn. So I have minus mg divided by cosine theta minus mu sine theta equals minus m vt squared divided by r. Just like before, my masses actually cancel out. Oh, I forgot to multiply by this, so by cosine theta mu plus sine theta. Okay, and again, I need to bring the r over here, so I'm going to multiply both sides by r, multiplied by r, and again, I can cancel out the r's. Okay, so I'm canceling out the r's, and I'm left with kind of a messy equation, but that's okay. I could hypothetically plug numbers in for all of these things. I have Vt squared is equal to RG, and then it's times mu cosine theta plus sine theta divided by cosine theta minus mu sine theta. Okay, and again, our very last step is to take the square root, so I'm just going to get rid of that squared, and I'm going to write VT is equal to the square root of RG times the square root of this whole fractional mess. Okay, but if you had numbers for the angle, if you had numbers for the radius, and you had numbers for the coefficient, you would be able to find that velocity.